In today's video, we're going to be taking a look at linked lists. And here we can see four variations of a linked list. We have a singly linked list, we have a doubly linked list, and here are circular linked lists, one with the singular linked list and one with the doubly linked list. So if we imagine that each one of these squares is a table, and inside of this table we have a key called next, and this key points to the next table, and this table has a key called next, and this also points to the next table, and so on. And once we get to the end of the list, the last table has a next value of 0. And if we now look at the doubly linked list, we can see that this is also a table with the key of next, but also has a key called previous. And this previous value points back to the previous table. So next points forward to the next table, and previous points back to the previous table. And if we look at circular lists, instead of pointing to 0 when we get to the last table in the list, circular lists point all the way back to the first table in the list. Okay, so now I've created a baseplate project, and inside of serve script service, I'm going to create a script and delete this print. And the first thing I want to do is let's just create an array so we can compare a linked list to an array. So first thing I'm going to do is say local array equals, I'm going to create an array of characters with A, B, C, D, E, F. And then I'm just going to simply loop through the array and print the values. So I'm going to say for index value in array do, and then I'm going to say print index and value. And if I now run the game, we should see it print 1A, 2B, and the entire array. Okay, let's now do this same thing but with a linked list. So first thing I'm going to do is say local link1 equals table, local link2 equals table, local link3 equals table, local link4 equals table, local link5 equals table, and finally local link6 equals table. Okay, so let's now connect all these links together. So link 1 is going to have a key called next, which points to link 2, and link 2 is going to have a key called next that points to link 3, and then link 3 is going to point to 4. So link 3's dot next is link equal to link 4. Link 4's next is equal to link 5, and link 5's next is going to link to link 6. And if we wanted to, we could say link 6 next is equal to 0. But I'm not going to bother setting this because doing this is essentially doing nothing. So here we have all our links now linked together. And let's now also set the values for our links. Now we can call the value anything we like. So we could say link1.data equals A, or we could call it, give it another key like value equals A, whatever we like. But I'm just going to use value. So link 1's value is equal to A, link 2's value is equal to B, link 3's value is equal to C, link 4's value is equal to D, link 5's value is equal to E, and finally link 6 value is equal to F. Okay, now that we've set up our linked list, let's loop through the linked list the same way we did for the array. But in order to loop through a linked list, instead of using the for loop, we're going to use a while loop. So the first thing we're going to need to do is have a value that points to the first link in the list. So I'm going to say link, local link equals link1. And then I'm going to say while link do, and then inside of the loop, I'm going to iterate to the next link. So I'm going to say link equals link dot next. And over here, I'm going to print the links dot value. And if we now run the game, we should see that first the array prints and then the linked list prints. The first difference you may have noticed between arrays and linked lists is that arrays have indexes. So we can see that for this array, there is a index value, and A is at a index of 1, B has an index of 2, C has an index of 3, and so on. Where on the linked list, there are no indexes. Another thing you may be wondering is which one of the two is better. And I would say try not to think as one being better than the other, but one being different than the other. So sometimes using arrays are the best option for the job, and sometimes using linked lists are the best option for the job. So arrays use indexes. So in order to access a certain value within the array, I must know its index. So for instance, if I want to access this C value, I must know that this C value is inside of the index of 3. So if I over here, I can say print array and use the index of 3 to access the C value. And for linked lists, in order for me to access this C value, I must know the link. So to access the C value, I can say print link3 dot value. So over here, I must know that the index is 3, and over here, I must know that this link is for this value. But if I don't know that the index is 3, I must use table find. So if I say table.find, and I'm going to search for the C value, and this is going to tell me the index that this C value is at. So the way find works, it's going to loop through the array, starting from the front, checking for this value to be equal to this value. So is A equal to C? No. It moves on to the next. Is C equal to B? No. Moves on to the next. Is C equal to C? Yes. Okay, so we're currently on index 3, and it's going to return the value of 3. So let's now make a find function for our linked list. So over here, we can say local function find, and we're going to search for a specific value, and we're going to loop through our linked list the same way we did over here. And then I'm going to, instead of just printing the value, I'm going to say if link.value equals value, then return link. Over here, we can get the link equals find, and with a value of C. But the thing is, if you're using a find function for a linked list, you're most likely using the incorrect list, and you should be using an array, because in a linked list, the link should be synonymous with the value, meaning that the value and link should be the same thing. And one way I can demonstrate this is, let's delete this and this. And let's imagine that I said local connection equals game get service run service dot heartbeat connect function end. So here we're connecting to a heartbeat event. This connect function returns a connection, which allows me to disconnect from the signal. So this connection, if we imagine that this was a link within the linked list, now I have a reference to the link. So I don't need to use table find to find the connection. I always keep a reference to the link, and that way when we disconnect from the linked list, this disconnect function doesn't need to find the value. It already knows what value the link is. Okay, let's now move on to removing an item from the linked list, and removing an item from the array. So let's say I wanted to remove this C value from the array. Well, first we need to know which index it's at, but let's just assume that we know that it's at index 3. All we do is say table.remove, and we say array, and we pass in a index of 3. And after I have removed the value, let's print all the values again. And let's comment out this print over here. And let's run the game. So what we should see is it prints 1, 2, 3, 4, 5, 6. And here we can see C is on index 3. And then we go through again on the second time. And A is 1, 2 is B. Now 3 used to be equal to C, but 3 is now equal to D. And 4 is now equal to E. And 5 is now equal to F. So we can see that D, E, and F will all move down one index. So what that means is when we do table remove with an index of 3, what Lua has to do is move the D index down to the C index. And then it moves the E index down to the D index and moves the F index down to the E's index. So what this means is if we remove the last index, which is index 6, this would be the fastest index to remove because there are no other items in front of it that need to be shifted down. But if we remove index 5, it would be slightly slower. And if we removed index 4, it would be slightly slower than that. And so on and so on. And index 1 would be the slowest index to remove out of all the indexes because it would have to shift all these indexes down 1 to take up the space of index 1. And the same is kind of true for table find. If I did table find, and if I search for the A key, this would be the fastest table find we could do because it would only need to iterate once to find the A key, where if I did table find F, this would be the slowest table find because it would have to iterate through the entire array to find the last value in the array. Okay, so let's take this find away and change this back to 3. So we're removing the C character. And let's now do table remove, but for the linked list. Now to remove an item in the linked list, it's very simple. So over here, link 2 point to link 3. All we need to do is change link 2 to no longer point to link 3, but to point to link 4. So it skips link 3. And if we now bring back this print and loop through it again, and let's comment out these two prints, and let's run the game. We can see it iterates through A to F, and then we iterate again, but this time there is no C. So you may be wondering, is it faster to do a table remove, or is it faster to update link 2's next value to link 4? And the surprising answer is it's faster to do a table remove in this case. So why is table remove so fast when it must shift D, E, and F down one index? And we can find the answer over here. So here we can see it says the last two operations are not particularly efficient, and it's talking about the table remove at an index of 1, as they must move elements up and down. However, because the table library implements these functions in C, these loops are not too expensive, and this implementation is good enough for small arrays. So in my personal benchmarks, I've noticed that table remove must shift around 500 indexes, so that means there must be 500 items after C in order for its performance to be equivalent to link2.next equals link 4. And let's say that we didn't know the index of C, so we had to use a table find like this. So if we did table remove with a table find, now this will always be slower than a linked list. But this will only be slower than a linked list if there are 500 items it must shift down. But let's step back for a second, because we are stressing over performance for no reason. Are we really scared about this little line of code? because I'm pretty sure we are doing things in our projects that consume a lot more performance than simply setting a key to a table. And if we're going to restrict ourselves to not setting keys into tables, we might as well just close Studio altogether. So when deciding to use an array or a linked list, the performance should not really be a deciding factor unless the array needs to be very long, for instance 5,000 plus items, and we must insert or remove from the front of the list. But in every other case, picking the array or linked list should be based on the features that each one provides. Okay, so now that we have a good idea of how linked lists work, let's create a class that uses linked lists. And the best use case that I can think of is an event system, but I'm going to create 4 event classes. One that uses bindable events, one that uses dictionaries, one that uses arrays, and one that uses a linked list. And then we can compare the 4 to see why one is better than the other. So inside of server storage, I'm going to create a module script, and I'm going to rename this table to be called class. And then I'm going to set the classes dot underscore underscore index equals class. Then we're going to create a new function. So I'm going to say function class.new. And this is going to create a self object equals set metatable. And it's going to have the class as the metatable. And then we're going to return self back to whoever called the new function. Then we're going to have 2 functions. So I'm going to say 3 more functions actually. Class. Now instead of using a dot, I'm going to use a colon here. So we can pass in self into this function. And this function is going to be called connect. And this is going to receive a function to connect to the event. And I'm going to create another function. And this one's going to be called disconnect, and this is going to receive a connection. And finally, I want another function called fire, and in this function we can pass any number of parameters. So we can use ... here to accept any number of parameters, and this is our basic class completed. So what I'm going to do now is duplicate this module script. So I have a total of 4 module scripts, and then I'm going to rename the top one to be called bindable event, the second one to be called dictionary event, the third one to be called array event, and the final one to be called linked list event. And now I'm going to go back into the script that we created originally, and I'm going to delete all this code that we created, and I'm going to require all 4 module scripts. So I'm going to say bindable event require game server storage, bindable event, and do the same for all the 4 modules. Okay, so let's first work on the bindable event class. And this is essentially just going to be a wrapper for Roblox's bindable event instance. So when we create a new bindable event object, we're going to create a bindable event instance and store it inside of the object. And then when we want to connect, we're going to say self.bindableEvent.event, and we're going to connect the passed in function to the bindable event, and we're going to return the connection back to whoever called this connect function. And when we want to disconnect a connection, we say connection.disconnect, like so. And when we fire the object, we say self.bindableEvent fire, and we pass any parameters into this fire. Okay, so now that we've completed this class, let's use it inside of our script and see how it works. So what I'm going to do is say local, and I'm going to call this bindable event, but I'm just going to use a lowercase b equals bindable event dot new. And then I'm going to connect 4 functions. So I'm going to say bindable event connect function, and what I'm going to do here is print A, and I'm going to connect another function to the bindable event. And in this one, I'm going to print B, and I'm going to do another one, print C, and I'm going to do one more and print D. I'm also going to reduce these down to a single line so we don't have so many lines taken up. And I'm also going to store the connection for all 4 of these. So I'm going to say local connection 1 equals, and I'm going to do the same for all 4. And call this one connection 2, connection 3, and connection 4. And now I'm just going to fire this event. So I'm going to say bindable event fire, and I'm not going to pass any parameters into this function. I'm just going to call it like this. And let's now run the game and see what happens. So the first thing you'll notice is that all these events get fired, but one thing you may notice is that they get fired in reverse order that they were connected in. So we can see that D got fired first, C was second, B was third, and A was the last. And if I put A at the end and then run again, now we can see that A gets called first, D gets called second, C, and then B. Now I'm going to explain why this is the case later on in the video, but for now we can see that everything's working fine. Okay, let's move A back to the top, and let's now work on our dictionary event. So let's open this script, this module script, and place it over here. Okay, so the first thing I'm going to need is, when we create self, we need a location to store all the connections. So what we could do, say self dot connections equals table. Now, we don't actually have to do this because self is a table itself, and we're not going to store anything else other than connections. So I could just store the connections directly within self and save the hassle of having a connections table within another table. So what I'm going to do is remove this, and I'm just going to add nothing into self and use self itself to store the connections. So I can reduce this down to this. Now the next thing I want to do is, in here I want to make a connection. So to do this, I'm going to say local connection equals a empty table. Then I'm going to use this connection as the index for self to store this function. So to do this, I'm going to say self and use connection as the index and store the function into self. And then I'm going to return the connection back to whoever called the connect function. And now inside of this connect function, we can use this connection table to find the index for this function. And I'm going to say self.connection equals nil. So it's the opposite of this. Here we add the function into self, and here we remove the function from self. And inside of fire, I want to loop through all the connections within self. So I'm going to say for connection, func in self, do, and then I'm going to use task.defer, because if we look into workspace, and if we look at the properties, Roblox now use a signal behavior of defer, no longer immediate. So what that means is bindable events use defer when firing. So let's just copy how bindable events work. So over here, I'm going to say task.defer, and I'm going to call the function, and any parameters that were passed into the fire function are also going to get passed onto that function. Now, one thing to take note is, because we're using task defer here, this is going to create a new thread for every function that has been connected to this event. Now, this is not that bad, but it's still not the most efficient way of doing it. There is a method of recycling threads to improve performance, but I'm not going to show you that right now. I'm going to show you that at the end of the video. Now, if you really wanted to have the best performance, we could just call the function directly like this, but this has a problem that if this function has a task wait or has a asynchronous function within it, it's going to block all the remaining functions from being called until the function has completed. Another downside is if one of the function errors, it's going to block all the other functions waiting to be fired. So I'm not going to do this for now. I'm just going to use the slow task defer method, but at the end of the video, we're going to come back and I'm going to show you how to recycle threads. Okay, so now that we've completed our DictionaryEvent class, let's move this to the side and let's come back to our script. And what I'm going to do is, instead of creating the 4 functions in here, I'm going to create the 4 functions at the top of the script. So I'm going to say local function, and I'm going to call this func1. And inside this function, I'm going to print a, and I'm going to reduce this down to 1 line of code. And then I'm going to copy and paste this 4 times. Then I'm going to say 2, 3, 4. And then I'm going to say print B, print C, and print D. And now, instead of creating the functions over here, I'm going to say func1, func2, 3, and 4. Okay, and I'm also going to change these connections to be called bindable connection. And I'm going to change the C to be a capital C. Okay, and now I'm going to do the same, but for the dictionary event. So I'm going to copy and paste. I think I'm going to do it over here. And instead of using the bindable event, we can use DictionaryEvent. I'm going to reduce this, change this to a lowercase d. I'm going to use connect. And this is going to be called dictionary connection 1, dictionary connection 2, dictionary connection 3, and 4. Okay, and finally, we want to fire the event. So I'm going to say DictionaryEvent fire. So we have the 4 functions. We create a bindable event, and we create a dictionary event, connect the 4 functions. We do the same on the dictionary, and we fire the event, and we do the same on the dictionary. And if we now run the game, we should see that the first 4 calls are from the bindable event, and we can see it goes in reverse order, D, C, B, A. And then it does the dictionary event, and we can see that this is in a random order, so it's C, B, A, D, and the order is not defined, so it could be different every time we run the game, or it could be different from one client to another client. Okay, so let's now make some more changes to mess things up even more. So what I'm going to do is create another function, and I'm going to call this func5, and it's going to print E. Then for connection 3, I'm going to make a custom function for each one. So I'm going to replace this with a new function and no longer use func3, and also have a custom function over here. And in this function, I'm going to print C just like we did before, but I'm going to connect func5 inside of this function. So I'm going to say, just like we did over here, I'm going to connect to the bindable event, but I'm going to connect func5. I'm not going to bother saving the connection, and I'm going to do the same over here, but I'm going to connect it to the dictionary event. Okay, so let's now run the game and see what happens. So what we can see is that bindable event is these 4 prints up here, and it prints in reverse order like it always did. And we can see that when C is printed, it connects this function 5 to bindable event. But even though function 5 was connected, we can see it doesn't print E over here. There's no E print. And if we look at the dictionary event, we can also see that this happens in a random order, and this also connected function 5 when it printed C, but we can also see that this also doesn't print this function 5 in E. Okay, so let's see what happens if I now fire twice. So let's copy and paste this over here. And let's do the same for dictionary event as well. So we're now firing twice for the bindable event and firing twice for the dictionary event. So let's now run the game. And we should see that it prints DCBA for this first fire, which is in the opposite order, which is correct. Then it prints DCBA again for this second fire, but we can see that it doesn't print function 5's E print. And then for the dictionary, it prints the 4 prints, but in a random order. That's this fire over here. And finally, it prints the 4 again in the same random order. So CABD, CABD for this fire over here. And we can also see that this also doesn't print E. So why does it not print E even though we're firing the event twice? And that is because we're using deferred. So over here for signal behavior, we're using deferred, which means that these connection functions are being deferred to be called after this current thread has completed. So that means that this fire and this fire get called first, and then these functions get called after both of these fire functions have been called. And the same is true over here. These two fire functions get called first, and then these connected functions get called after this current thread has completed. Okay, let's now change this signal behavior. So over here where it says signal behavior, I'm going to change it from deferred to immediate. And I'm going to go inside of our dictionary event, and over here where it says task defer, I'm going to change this to task spawn. So it now matches the workspace option. And if we run the game again, let's see what happens. So in this first fire, it prints DCBA, the same like before. Nothing has changed. But now we can see in the second fire, it prints EDCBA. So now, because these connections fired as soon as we called fire and were not deferred, this fire happens after this connection was added. So this fire now includes the E print, unlike before where it didn't include the E print. So we can see that by changing the workspace's signal behavior from defer to immediate, changes how this fire function works. But even though it's slightly changed, it's still working correctly, because we would expect that if this fire happens immediately, that this connection will be added, and if it was deferred, then it wouldn't be added, and the outcome is how we would expect it to be. But let's now look at the dictionary event. So the dictionary event is all these characters over here. Now we can obviously see that something is not right. We can see it printed B, B, and B 3 times when it should only print B 2 times. We can see that C also got printed 3 times. We can also see that E got printed 2 times down here. So what I'm going to do is comment out all these fires and just keep one dictionary event fire. And I'm going to run the game again. And we can see it's still messed up. C got printed twice. E got printed. Now let's stop and run again. This time we can see E got printed again. Let's stop and run again. And here we can see that E never got printed this time. Now the reason it does this is because dictionaries internally work like linked lists, because you may be aware of the next function and you pass in the dictionary and it will tell you the next item in the list. So it works a lot like linked lists. But the problem is we don't have no control of the order that Lua placed the linked list in. So what this means is when we add the function to this dictionary, the order of the linked list changes, internally all the next functions start to point to different locations. So when we had this C function over here, it inserted the new connection, and then instead of C pointing to nowhere, now C's next points to A. So it goes back up to the top of the linked list, and then now A still points to D, which it did up here. Look, A pointed to D, so A pointed to D, then D points to C, where it should be that D points to B, but that got changed. So we can see that if we add items into a dictionary while we're iterating through the dictionary, it messes everything up. We cannot insert items into a dictionary while we're in the middle of looping through them. Now, if we change this back to defer, then what's going to happen is it's going to loop through the entire dictionary before any of these functions ever get called. So that way it does work because this iteration has completed by the time this function gets even called. So using deferred here works correctly, but using spawn here doesn't work correctly. Or even if we didn't use task at all, if we just called the function like this would also not work, because it would add items to this dictionary while we're iterating through the dictionary, and that's not allowed in Lua. So we must use defer here if we want this dictionary to work correctly. Okay, so now that we've changed dictionary back to defer, let's also change workspace back to defer. So signal behavior from immediate back to defer. And let's go back to our script. Now we've tested what it's like when we connect a new function during iteration, but let's see what happens if we disconnect a connection during iteration. So I'm going to bring back this fire. I'm going to delete this second fire and delete this second fire. And then I'm going to comment out the connects. And what I'm going to do is say bindable event disconnect, and I'm going to disconnect the second connection, and I'm going to do the same over here for the dictionary. So dictionary event disconnect dictionary connection 2. So if we now run the game and have a look at what's happening, so we can see that it prints D. It doesn't print E because we never added function 5 to the connection. And after D, it prints C. And during C, we disconnect connection 2, which is function 2, which prints B. And here we can see it no longer prints B, and B was skipped, and then it printed A. So this fire printed D, C, and A. So how come this disconnect is working instantly during iteration, while this connect never worked instantly during the iteration? So if I add this connect back in and run the game again, we should see that this function 5, which prints E, never got called. And that is because when we connect to a bindable event, Roblox adds this connection to the top of the list. Remember, it prints in opposite order, so it would print E, D, C, B, A. Well, we're already past E, so we're currently at C. But this connection 2, which prints B, has not been reached yet. We're still at C when this connection is disconnected. So after C, instead of going to B, because it's been disconnected, it no longer goes to B. Now, if we changed this to be connection 4, which is the D, now because D is before C, D would still get called even though we disconnected it. But if we disconnect connection 2 or connection 1, then it will disconnect it during the iteration. And let's change this back to how it was. So let's change this back to 2. And let's now look at the dictionary. So here is the dictionary part. And we can see that the order is random again. But we can see that all 4 get printed even though we disconnected from it. And That is because we're deferring. Remember, when we defer, this loop iterates first and then these functions get called. So any changes that are made in this function only happen after we have already finished iterating. Okay, so let's now go back to spawn and see how our disconnect functions work during if we have it set to spawn. So inside of workspace, I'm going to set signal behavior from deferred to immediate. And inside of our dictionary event, I'm going to change task.defer to spawn. And if we now run the game, we can see that the bindable event works exactly the same. Nothing has changed. It's DCA. B is removed instantly, just like it was when it was set to deferred. But if we look at the dictionary, this time it did CAD, and we can see that B was removed. But if I stop and run the game again, this time we can see that it did print B. So the reason for this is because the order that the dictionary fires is random. If B gets fired first, then B gets called. But if C gets fired first, then B doesn't get called. So we can see in this case, B got called first. And so when we disconnected in C, B had already been called. But if we stop and try again, we can see that this time C must have called first. Now I don't know if B was going to get called after C or after A, but whatever the case is, because C got called first, B never got called. Okay, so let's now quickly overlook what we've learned about using dictionaries for a event class. The first thing we learn is when iterating through the connections, the order of this iteration is undefined. So the order that these connections are going to get fired is random. The next thing we learn is we cannot insert new connections into the dictionary during the iteration, but we can remove connections from the dictionary during iteration. Now, because we cannot insert items into the dictionary during iteration, and this is a very important ability to have for our event system, the only option we have is to always use task defer. So we have no other option but to use task defer here. We cannot call the function directly, like so, and we cannot use task spawn. Now, when I say using task defer is our only option, it's not technically our only option, but it's our only viable option because there are other methods of doing it. So for instance, let's comment out this loop. And what I'm going to do is make a clone of self. So I'm going to say local clone equals table dot clone, and I'm going to clone self. So this is going to create a new table, a new dictionary that contains all the connections. Then, just like we did here, I'm going to loop, but instead of looping through self, I'm going to loop through the cloned dictionary. And now we can call function while iterating, like so. And now even if we connect to self, because we're not connecting directly to this cloned dictionary, it's not going to break this cloned dictionary. So we can call the fire function like this, but this is not very performant because we have to create a clone of self every time we call fire. And we could also use task.spawn here if we wanted to, like so. But I would not really recommend cloning self every time we call fire. So that's why I say that using task defer is the only viable option. Okay, so let's now make our ArrayEvent class. So let's open up ArrayEvent. And I'm going to move the dictionary to the top right. And what we're going to do is, just like we did for the dictionary, I'm going to use self as the array to store all the connections. I'm not going to have a separate table within the object, so I can just return the self object directly like this, the same way we did over here. And then, just like we did for the dictionary, I'm going to make a connection. And then, unlike dictionary, instead of using self and the connection as a key, I'm going to use table.insert, and I'm going to insert the connection into self, like so. So we insert the connection into self using table insert, and this is going to insert it at the end of the array. Now, we can't store a function in the array as well, so we have to store the function within the connection. So I'm going to store the function as index 1. We could give it a key like this called function, but I'm just going to store it as at index 1. And finally, we want to return the connection like so. Now, in order to disconnect, we're going to need to use table find to find the connection at which index it's at, and then we're going to use table remove. So I'm going to say table.find, and I'm going to search within self, and I'm going to search for the connection, and this is going to tell us the index. Now, if this connection cannot be found within the table, within self, it's going to return nil. So I'm going to say if index equals nil, then return. And finally, if it does find the index, I'm going to use table remove self index. And finally, we're going to loop over self inside of fire. So I'm going to say for index connection in self do. So it's a lot like over here, but over here we receive the connection and function as the value and the connection as the key, where over here we'll receive a index because it's an array, and we receive the connection as the value. So what we need to do is now fire the function. I'm going to use task.defer, and to get the function, remember it's stored as the first index of the connection. So to get the function, we do connection index 1, and we want to pass the parameters that are passed into fire over here. Okay, so let's now move this to the side, and let's now use it inside of our script. So what I'm going to do is comment out all these, but before I do that, I'm going to copy and paste one of them and comment out the other two. And I'm going to change this to ArrayEvent, and change all these to ArrayEvent, and comment out this. And I'm going to change all this to array connection 1, array connection 2, array connection 3, array connection 4. And let's not also forget this bindable event here, to change this to ArrayEvent connect. Okay, let's now run the game and let's see what happens. So we can see everything worked correctly. It prints A, B, C, and D. Now, unlike bindable events, it did not print in reverse order. It printed in the same order that we connected. And unlike dictionaries, it was not in a random order. Okay, let's now see what would happen if we disconnect array connection 2. So let's disconnect array connection 2 after we print C and press run. And we can see that everything ran like normal. And even though we disconnected connection 2 already ran anyway by the time we printed C, so it wouldn't have cancelled it in the first place. But let's see what happens if we disconnect connection 4. Now, in order to disconnect connection 4, we have to make the variable up here and set it over here. That way we won't get an error when referencing this connection. So let's now see what happens when we disconnect connection 4. And we can see that even though connection 4 ran after the C print, we can see it still printed D, and that is because we're using task defer. So the same thing is happening that happened in the dictionary event system. Because task defer is going to defer this function call to run after we have already finished looping through the array of connections. Okay, let's change task defer to task spawn. And instead of disconnecting connection 4, let's disconnect connection 2, which is the B print, and let's run the game. So what we can see now is it prints A and B, which was disconnected, but that wasn't disconnected just yet. We disconnected it when we printed C, but connection 4, which is meant to print D, never got printed. So why is disconnecting B stopping D from being printed? So what's happening here? So what we're doing is when we call the fire function, we're looping through the array and calling the functions. So we're looping from A, we call the A function, we loop to B, we call the B function, we loop to C, we call the C function. Now when we call the C function, we're using disconnect, and disconnect uses table remove. So what that is doing is we're removing connection 2. So that means we're removing this B connection. Now when we use table remove, remember that all the indexes in front of B get shifted down. So C is going to be shifted down to this index, to the second index, and D is going to be shifted down to replace C's index. Now we're currently at this index in our loop. So when the loop continues and tries to go to the next loop, D is no longer there. D has been shifted down into C's position, and because D is no longer in index 4 but index 3, we can see that D never got printed because it's been moved up into C's index. So let's now see what would happen if we disconnect connection 4 instead of connection 2. And let's now run the game, and we can see that everything works correctly. So if we disconnect a connection that's higher than connection 3, everything will work correctly. But if we disconnect anything that's equal or lower to connection 3, then it won't work. So let's test connection 3. So I'm going to define connection 3 up here, and I'm going to change this, remove this local, so it uses this local up here, and then I'm going to disconnect connection 3 inside of connection 3. So this is kind of like the once connection. And if we now run the game, we can see it prints A, B, C, but doesn't print D, even though we never disconnected connection 4. So we have the same problem that we had when disconnecting connection 2. Okay, so now that we've tested disconnect, let's see what happens if we use connect during connection 3. And I'm not even going to bother testing defer here, because we always know that using defer will solve our problem, because when we defer, this function call is going to be deferred to be called after we've iterated through the entire array. So let's just skip defer and use spawn straight away, and let's run the game. So what we can see is that because we connect and because we're iterating through from top to bottom, from A to E, from A to D, and when C gets called, it connects function 5, and because we still haven't reached the end, function 5 gets called. So unlike bindable events, because bindable events get called in the opposite direction, E would not get called for bindable events, but for arrays, because we're looping through them in order, now E gets called as soon as we connect it. So you may not like the fact that E gets called even though it gets connected after we have called the fire function. So in order to solve this problem, we can do the same thing that bindable events do. We could iterate through this connections array in reverse order. So to do this, I'm going to comment out this loop. I'm going to say for index equals, and I'm going to use, we're going to loop through self down to 1 in increments of -1. And now we can just do task.spawn self using the index. And remember, the function is stored in index1. We can see that over here. Index1 stores the function, and we can call it just like this. So we can do this to iterate through the connections forward, or do this to iterate through the connections backwards. So if we now run the game again, we can see that it loops from D down to A, and even though we connected connection 5, because we're iterating in the opposite order and E was added to the top, we can no longer see E being called on the first fire. But if we fire twice, now we can see that E doesn't get called on the first loop, but it does get called on the second fire. Now we have to be a little careful with arrays when inserting them while we're iterating through them. In our case, adding this connection has no problems because we're inserting the connection to the back of the array. But let's see what would happen if we inserted at a position of 1. Let's actually remove this second fire so it's not so confusing, and press 1 again. So what we can see is it says A, B, C, and D was missing. So why is D missing? So let's go through this to see why D is not being printed. So when we insert connections to the front, so we first insert A, which places A at the front, then we put B, which goes ahead of A, then we put C, what puts C ahead of B and shifts B and A up, then finally placed D into the front. So now we ended up with an array in the reverse order, so it goes with D, C, B, A. But when we fire, because we're looping from back to front, that's why it looped from starting from A, because we started from the back of the array. So it first prints A, and then it goes to the next index, which is B, and in B it prints B, which it did over here. Then it goes to the next index and prints C. Now inside of C we connect connection 5. So what is that doing? That's adding connection 5 to the front. So E is getting added at the front of the array, and this is causing all the other items to be shifted forward to make room for E. So D goes forward, C goes forward, B goes forward, and A goes forward. So now when we loop to the next iteration, because D has been moved into position C, D gets skipped and we go straight to E. So D never gets printed, but E does get printed. So we can see that inserting, if we insert from the front, this causes a problem, but if we insert to the back, this doesn't cause a problem. Okay, let's now try to summarize everything we've learned about arrays. So if we're iterating forward through the array, so from A to B to C, now let's say during C we want to insert or remove, what this means is it's safe to insert or remove. So let's put a green box around where it's safe. So it's safe to remove for these indexes. We can insert or remove anywhere here if we've iterated up to C, but we cannot safely remove from indexes 1 to 3 during the iteration. And if we're iterating backwards, so from F down to E, down to D, and down to C, so let's say we're currently at C, now what this means is it's safe to insert and remove from these indexes, but it's not safe to insert and remove from these indexes. So let's now overlook DictionaryEvent and ArrayEvents and compare the two. So if we're using task spawn for both classes, then what this means is it's not safe to use connect on the DictionaryEvent, and it's not safe to use disconnect on the ArrayEvent. Now, sometimes it might not be even safe to use connect, but because we're always connecting to the back of the array, this makes it a safe operation. But if we was connected to the front of the array, then connection would also not be a safe function to have. But because we're always connected to the back, this makes the connect function safe. So dictionaries don't have a safe connect function, and arrays don't have a safe disconnect function. But if we change task spawn to task defer, then this makes both arrays and dictionaries safe in all cases. Okay, let's now move on to our linked list class. So I'm going to close ArrayEvent. I'm just going to put DictionaryEvent to the side so we can use it as a reference, and open LinkedListEvent. Now in here, we're not going to store anything into self just yet. So we don't have to store it in a local variable. We could just return it instantly like we did for the other classes. And now when we call connect, we're going to create a connection just like we did over here. Now we need to remember that this connection is not only going to be the connection, but it's also going to be the link in the list. So remember that this connection is both a link and a connection in one. Now what we're going to do is we're going to add this connection into self, but we're going to point to it. So we're going to say self.first equals connection. So this is saying that the first link in the list is this connection over here. Okay, now then I want to store this function inside of the connection as well. So I'm not going to store it in index 1 like I did for arrays. I'm actually going to give it a key this time. So I'm going to call it function equals func, like so. And then I'm going to return the connection. Now this works fine for the first connection, but doesn't work for the second time we connect, because we're losing the old connection when we overwrite the first value inside of self. So what we need to do is shift all the other connections onto the end of this connection. So to do this, I'm going to say next equals self.first. So anything that was linked, the first link that was on first from before, gets added to the end of this new connection, this new link, and then this new connection becomes the new first. Okay, so what we want to do now is disconnect the connection. Now in order to disconnect, what we need to do is we need to find the connection, the link before this link, and update its next value to point to this value's next value. So to do this, we must loop through the linked list to find the previous connection. Now in the future, we're going to be using a doubly linked list, and that's going to allow us to not have to loop through the connections to find the previous connection. But for now, let's loop through it, and I'll show you this way with a singly linked list, and then we'll update it to be a doubly linked list so we can see how it works when we have a doubly linked list. So let's first loop through the links. So I'm going to say local link equals self.first. Then I'm going to say while link do, and I'm going to say link equals link dot next. So just like we did at the start of the video, we loop through every link inside of this linked list. And now inside of this loop, what I'm going to do is say if link dot next is equal to connection, then I'm going to say link dot next is equal to connections dot next. So if the next value, this link points to this connection, no longer make it point to the connection, but make it point to the connection's next connection. So it's going to skip this connection. And once we've found the connection, there's no point continuing the loop. So we can just return out of the function and break out of this while loop. But this code currently has a problem because we start at the first link and the first if check checks the next item from the first link. If this connection is the first link, this while loop is not going to find the connection. So what we could do is say over here, if link is equal to connection, then, and then have an else. So if it's not the first connection, we loop through the linked list. But if it is the first, then we can update the first to say self.first equals connection dot next. But there is a better way we can make this function, and that is by changing the the key from first to next. So instead of this being called first, let's rename it to be called next. So that way it's going to match the key inside of the links. So the object, the linked list object, has a next value, and the keys, the links, also have a next value. So now what we can do is make a simplified version of this. Let's comment this out. So just like we did over here, we're going to get the first item in the link, but the first item is going to be the object, not the first link. So we can just do this, link equals self. Then we're going to loop through like so and say link equals link.next. Now, because this is called next and this is both called next, this next here is going to work for both the object and for the links. And now we can have this check over here, like so. And we can do this over here, like so. And do this, like so. So this and this do the exact same thing now. Okay, so now let's delete this old code. And let's now do the fire function. So in the fire function, we're going to loop through the linked list again, but so it's almost like disconnect, but we are going to start from the link, not the object. So I'm going to put a next here. So this first item is a actual link, not the self object. And then I'm going to do a while do loop again. And I'm going to say link equals link next. So over here, we're going to call the function. So I'm going to say task.defer. Now we always know that defer fixes any problems we have. So I'm just going to change this to spawn so that we can see if we do have any problems. Because if we use defer, it always masks any problems that we have. So let's just use spawn here. And I'm going to spawn the links function, which is this key over here. And I'm also going to pass in the parameters that get passed into the function, like so. And there we have it. So we now have a event system that uses a linked list. Okay, so let's now close the dictionary event and move the linked list to the side. And then let's open our script again and let's comment out the array. But before we do that, let's copy and paste it and comment out the old version. And let's now use do the same thing, but this time with the linked list event. So I'm going to replace this with linked list event. This is going to be a linked list event with a lowercase l. Then I'm going to connect function 1, function 2, this custom function. Replace these. I'm also going to comment these out. I'm going to connect this as well. And also fire from the linked list event. And I'm also going to replace the connection names to linked list connection 1, linked list connection 2. Let's also replace these two up here. Linked list connection 3 and linked list connection 4. And let's replace these as well. Okay, so we now have our linked list. So let's see if it works. So what we can see is that we loop from D to C to B to A. so it loops in reverse order. And that is because when we connect a new connection to our linked list, we add it to the front of the list and then we shift everything down. So when we added A first, it was at the front. Then when we added B, B got added to the front and was shifted to go behind BB's next. And then when we added C, C was added to the front and B became C's next. So the list gets added backwards. So this works a lot like how Roblox bindable events work. Now, one thing we could do to visualize this in another way is if I comment out the fire and just print the linked list event and run the game again, what we should see is we have the linked list object, and this object has a next value which points to the first link in the list. And here we can see the function that's stored inside of the link. And this link also has a next value which points to the next link. And this has a function, which is the next connection. Then this has a link to the next link. This has a link to the next link. And this final link doesn't have a next value. So we can see that this first link would be D. This one over here would be C. This one over here would be B. And this final one over here is going to be A. Okay, so let's now remove this print and bring back the fire. And this time, let's disconnect connection 2 when we reach link 3. So let's change this to connection 2. So when we print C, we're going to disconnect this one over here. So let's run the game. And what we can see is it goes in reverse order. So it starts at D, then C, then B was removed, and then it went to A. So it does remove it instantly during the loop. So it works just like bindable events. So let's now see what would happen if we remove our own connection when we're iterating through it. And let's run again. And we can see that it works fine. So it loops from D to C to B and then to A. So there was no problems. And let's see what would happen if we disconnect connection 4. So let's run again. And we can see everything works fine. It loops from A to B to C to D. So it currently is working just like bindable events. Okay, let's now test adding connections. So let's comment out this disconnect and add function 5 and run the game. And we can see it prints from A to D, and connection 5 was not printed. But if we run the fire a second time, we can see that the first loop didn't print E, but the second loop did print E. So it's running just like bindable events. So bindable events and our linked list class work exactly the same now. Okay, so let's quickly overview all our 3 classes. So first thing we need to know is when we use task defer, it masks our problems, but using task defer may not always be an option. Now for an event system, using task defer is a viable option, but if you're making something else, or you need to iterate through a list and you want to insert and remove items without having the need to defer, then we know that for arrays, the insert and remove may not be safe, and for dictionaries, only removing is safe, but inserting is never safe. But for linked lists, inserting and removing from a linked list is always safe. So that is one of the main benefits of linked lists. The ability to insert items and remove items while we're iterating through it is one of the major benefits of a linked list. Now, currently, our connect function for our linked list and our array have roughly around the same performance. There's nothing major going on here, but for our disconnect function, the array must first find the connection, and then if it exists, remove it. And we're doing the same over here. We loop through every link, trying to find the connection, and once we've found it, we remove it. But what we can do is to outperform arrays here, we could have a doubly linked list, and this will allow us to disconnect a connection without the need to find it. So let's now update our linked list to be a doubly linked list. Okay, so what we're going to do is first close the dictionary, and I'm going to move the array to the right. And what I'm going to do is, before we set the object's next value, which is the first link in the list, I'm going to check to make sure, see if there's another item at the front. So I'm going to say if self.next is not equal to nil, then, so if there is already a linked list existing at the front, I'm going to say that this self.next.previous is equal to the connection. Okay, now let's go back to our script, and let's remove this fire and comment out one of the fire, and let's just print the linked list, and let's also comment this out, and let's see what happens when we run the game. So we can see the first table, and it has a next, which points to this table, and this table, we can see it has a previous that points back to this item over here. And it doesn't tell us, it says it's a cyclic table because it's already printed this table, so it's not going to print it twice. And it has a next and a previous, and this previous points to this table. And this doesn't have a next, but it does have a previous pointing up to the previous table. So we can see that by adding this line of code here, we now have a previous value stored inside of each link. Okay, so now that we have a previous value stored in each link, let's comment out the old disconnect function, and let's make a new one that takes this new previous value into consideration. So the first thing I'm going to do is say if connection.previous is equal to nil, then that means that this connection is the first connection, so it's the self.next connection. So what we need to do is update self.next to point to connections.next. Now another thing we need to do is connections.next is previous needs to be set to nil, so it no longer points to this connection over here. So I'm going to say if connection.next, then connection.next.previous, which used to point to this connection, should now point to nil. Okay, so if our connection does have a previous, so what I'm going to do is add a else here, and I'm going to say connection.previous.next equals connection.next. So the previous connection, which used to point to this connection, is now going to point to the next connection. And then I'm going to do the same, which I did over here. I'm going to say if connection next, so if we do have a next connection, then connection next.previous, but we're not going to set it to nil, we're going to set it to be the previous connection, like so. So the previous connection's next is going to be equal to our next, and our next, if it exists, our next previous is going to now equal to our previous. So now we've disconnected this connection without the need to loop through the entire list. So we can delete this, and now we have our new disconnect function. So in order to see this working, what I'm going to do is go back into our script, and I'm going to simplify this greatly. So I'm just going to pass in function 3 here, and I'm going to remove this fire, and I'm going to change these back to local. Okay, so what we're doing is we're connecting functions 1, 2, 3, and 4. Then we print the linked list, and then I'm going to disconnect. So I'm going to say linked list disconnect, and I'm going to disconnect connection 3. And after I've disconnected, I'm going to print the linked list again. So let's now run the game and let's see if it worked correctly. So we have a next, which is the object. It's not a link. Then we have our function with a next value that points to the next link. Now this link has a next and previous, which points to the next function. And it keeps going all the way up. So we have 1, 2, 3, 4 functions. And we connected 1, 2, 3, 4. Okay, so now if we check this other one, we should see that we now have 3 functions. So one of the functions was removed, we can see, and everything seems to work fine. And just to be double sure, what I'm going to do is change these prints, and I'm going to do the fire function, and I'm also going to fire it again after we have disconnected and run again. So we should see it loops in reverse order, starting from D, C, B, A, and on the second time we fire, it goes from D, it skips C because C was disconnected, and then it prints A, so B and A. But the thing is, we can kind of simplify this disconnect function even more. So let me show you how. So if we go back and print the linked list and run the game. So we should see that the object has a next value, which points to the first link. And this doesn't have a previous value. But what if we did add a previous value that pointed back to the object? By doing this, we can simplify our disconnect function. So let me show you how we can do that. So over here, when we create the object that's going to be added to the front, I'm going to say previous equals self. So this first object that doesn't have a previous currently is now going to have a previous that points back to the self object. And if we now run the game again, we should see that the object has a next value, but the first link in the list now also has a previous value where previously it didn't. So now we can get the object from this value over here. So now that this first link has a previous value, we no longer need to check if previous is equal to nil, because every connection always has a previous value. So all we need to do now is just this part of the code. So I can just copy and paste this, and this is all we need now to disconnect a connection. We no longer need to do this. So I can remove this, and here's our new simplified disconnect function. Okay, so we've finished our linked list event class, but if you remember from earlier on in the video, I said that spawning a thread for every function in the linked list is not as efficient as it could be, and there's a technique for recycling threads to improve performance. So let me now show you how to do this. Now this has nothing to do with linked lists, but you can imagine it as some bonus content for this video. So the first thing we're going to need is to create an array which is going to store all our threads that are currently recycled and are ready to be reused. So at the very top of the module, I'm going to create a new array called threads, and it's going to equal to an empty table. And then I'm going to create a new function. So I'm going to say function thread, and this is going to be our thread function. And so if we don't find a thread inside of the threads table array, we're going to create a new one using this function. So what I'm going to do is I'm going to comment out this task spawn, and the first thing we need to do is check to see if there's a thread inside of the threads array. So I'm going to say local thread equals table.remove, and I'm going to remove the last item from the threads array. Now, because it's removing from the end of the array, it's very performant. We're not removing it from the front of the array, so we don't have to worry about that. And then I'm going to say if thread equals nil, then else. So if the thread does not exist, we're going to create a new thread. If the thread does exist, we're going to reuse the old thread. So if the thread doesn't exist, what we're going to do is we're going to use task. Now we could use defer or spawn, but I'm going to do it with spawn for now. And we want to call this thread function inside of the spawn function. And we want to pass the function, the links function, to the thread. And we want to extract this function. And then we also want to pass the parameters that were passed in from fire. So we want to put a ... here, and we also want to get the ... over here. Okay, so if there is no thread, we spawn a new one, but if there is a thread, we can do pretty much the same thing. So we're going to do task.spawn, and we're going to pass in the thread into the task spawn, because here we can see it says task spawn accepts a function or a thread. So we can pass in the function or we can pass in the thread. And we're going to do the same thing. We're going to pass the function, and then we can also pass in the ... Okay, so when we create this new thread, it's going to call this function, and the first job of this thread is to call the function and pass it the parameters. So over here, I'm going to say func ... And now if we just left it like this, this thread would, after this function completes, this thread function will also complete, and this thread would be garbage collected. But we don't want to do that. We want to keep this thread alive in a yielded state and place it into the threads array. So what I'm going to do over here, I'm going to say while true do. So we create a infinite loop, and then I'm going to do a quarantine.yield. Now when we do a quarantine yield, it's going to yield this thread until we use a task spawn on it. But currently we have not added this thread into the threads array. So what I'm going to do over here, I'm going to say table.insert, and I'm going to insert into the threads quarantine.running. So this is going to get this thread and add it into the threads array. And once we've added it, it's going to instantly yield, waiting for someone to wake it up using the spawn function. So when we wake up this yield over here, we pass the function and parameters to this yield function. So this yield function is going to receive the function and the parameters, but we cannot use ... here. So for now, I'm just going to use P1, P2, and P3 just to represent ... But in the future, I'm going to show you how we can make it work with ... So if the thread does not exist, we create a new thread, we pass in the function and the parameters, and this thread calls the function. Then it starts an infinite loop, adds the thread to the threads array, and then once it adds it to the threads array, it yields. And then while it's yielding, if someone else fires an event, it's going to get the thread from the threads array, it's going to wake it up and pass the function and parameters again, which get received over here. So over here, we must call the function again, this new function that we've received, and we must pass the parameters which would be ... but for now we're just using P1, P2 and P3. And then once this function completes, it's going to loop back, get inserted back into the threads, meaning that it's ready to be reused again, and it's going to start yielding again. And it's going to keep going, waiting over and over and over again. So we're going to keep recycling this thread over and over. Okay, so before we go about testing this new thread that we've created, it's possible to simplify this code slightly. So instead of doing it like this, what we could do is we could say task.spawn, and we could use table.remove directly inside of here to remove the thread. But if the thread does not exist, we could say or and pass the function like this. And then all we need to do is pass the function and parameters like this. So now this code is the exact same as this code, just simplified. So let's now delete all this and just keep our simplified version. Okay, so let's now move this to the side. And let's go back to our script. And what I'm going to do is I'm going to delete all this. And I'm also going to delete all this. I'm going to delete all this. Just keep one connection. And I'm also going to delete this print. And we can keep these requires. So I'm going to create a new linked list event, and then I'm going to connect a single function. Now over here we're going to receive the parameters, but I'm just going to use ... so we can receive all the parameters that are passed into this event. And then I'm just going to print ... to print whatever values are passed into this event. And over here I'm going to fire the event, and I'm going to pass A, B, C, and finally D. And then I'm going to fire again, but I'm just going to make one small change. So at the front, I'm going to pass 1, and on this one I'm going to pass 2, and on this one I'm going to pass 3. Okay, so if we now run the game, we should see that it passed 1 A, B, C, D for the first fire, but for the second fire and third one, it only passed 2 AB and 3 AB. And that is because we're only passing 3 of the parameters when we wake up the yield. So we can actually see that the first time we fire, it creates the thread, which was able to pass all the parameters because we was able to use ... But for the second and third time we called fired, it recycled the thread, which ran down here, which only passed 3 of the parameters, which never ran this part up here. So now we can see that we are actually recycling threads. Now inside of this connection, if I add a task wait and run the game again, what we should notice is now that we've created 3 threads and haven't recycled the first thread. So we can see now, instead of only printing 3 parameters like it did before, for all 3 fires it printed all the parameters. That means we created a brand new thread for every fire. And that is because we have a task wait here, which is preventing this function from ending. And because this function is in a waited state, this part where it inserts the thread into the threads never got reached by the time we called the second fire. So when we try to remove the thread from the threads array, it had not been inserted yet into the threads array, so it had to create a new thread. And when we tried to fire again, because that thread also waited, there was no threads inside of the threads array, so it had to create another thread. So now, after these 3 fires, we had 3 threads inside of our threads array once these waits completed. But if we add a task wait here, and if we call 3 more fires after the wait and run the game again, what we should see is that the first 3 over here never recycled threads, so we created 3 threads. So now have 3 cached threads in our threads array. Then after the wait, because these waits were completed by the time this wait completed, now these threads, the 3 threads that we created in these 3 fires, were inserted into the threads array. So by the time we do these 3 fires, it was able to recycle the 3 threads that we had created up here. So we can see that no threads were created for these 3 fires. So these 3 fires would be a lot more efficient than these 3 fires because it could recycle the threads. But if we remove this task wait from inside the connection and run the game again, now we can see that it only creates 1 thread and all other fires share the same thread. So only 1 thread was created this time. But if we change task spawn to task defer, and if we run the game again, we can see it goes back to like it was when we had the wait, even though we don't have the wait anymore inside of this connection. So the reason for this is because we're deferring the thread from running, when we call these 3 fires, the thread has not run yet. So these 3 fires run one after the other, and then once we get to this wait, this thread will run and get added to the threads array. So by the time we get here, we're no longer deferred, and now we can recycle for these 3. So if we use deferred, there must be a delay between fires in order to detect that this thread was added back into the threads. But if we use spawn, it will instantly spawn the thread and allow, and if that thread does not yield in any way, it could instantly go back into the threads array, allowing the second event to instantly use the same thread. So if we summarize, if we use task spawn, the threads array will most likely stay shorter, but if we use task defer, then the threads array will most likely get larger, but the amount is not going to be that great, so it's nothing we really need to worry about. So if you want to use defer, then use defer, but if you want to use spawn, then use spawn. I wouldn't really worry about how many threads get cached in the threads array. It should be okay. So let's now solve the problem that when we wake up a yielded thread, only 3 parameters can get passed to the function and not all 5 of them here. So there are 2 ways we can do this. There's the slow way and there's the fast way. I'm first going to show you the slow way, and then I'm going to show you the fast way. So what we're going to do is when we yield, instead of getting the values from the function like this, we're going to convert the parameters into a table. So let's comment out these over here. And what I'm going to do is say local t equals. Now to convert this to a table, there's 2 ways we can do this. We can use table.pack and then pass the yield function into table pack. So when this returns properties, it's going to get packed into a table. Now another way we could do this is just to put the brackets around quarantine yield like this, and this will also create a table. Now if we print t like so and run the game, we should see that for the first time when the thread is created, it calls the function, which is this part over here, and then for the recycling of threads, it just prints the table. And if we look inside of the table, we can see index 1 is the function, 2 is the first parameter, 3 is the third parameter, second parameter, and third, fourth, and fifth parameters. So what we need to do now is we need to extract the function from the front of this table. So to do this, I'm going to say local func equals table.remove, and I'm going to pass in the table, and I want to remove the first index Now, if you remember, removing the first index is the slowest one we can remove because it has to shift all these other values up a index. So now that we have the function, what we can do is call the function, and to pass the remaining parameters, what we need to do is say table.unpack t. So any remaining parameters inside of this table are going to get unpacked and passed into this function. So let's remove this print, and let's now run the game, and we should see that it works correctly. And here we have it. This is the slow method of passing all the parameters from quarantine yield into a function. Okay, so let me now show you the fast method. So the first thing I'm going to do is delete this comment, and I'm going to comment out the slow method. And the first thing I'm going to need to do is create a new function that looks just like thread. So let's copy and paste the thread function, and I'm going to call this function call. And all this function is going to do is call the function. And now all we need to do is over here call this function and pass quarantine yield into this function as parameters. So this is going to be able to extract the function from the front and also receive the ... so it works correctly. So now if we run the game, we can see it works correctly, and we don't have to worry about converting it to a table, then removing the function from the front of the table, and then unpacking the table back into parameters. And let's now finally remove the slow method, and we've now completed thread recycling, and our linked list event system has been completed. So hopefully this video has helped you understand what a linked list is, how to create your own linked list, and some of the benefits of using a linked list. But if you don't want to create your own, but I do recommend as a new scripter, it's a good idea to practice making linked lists. I think it's a very good exercise for improving your scripting skills, but I have created my own linked list module. So let's now take a look at my module. Okay, so I've created a brand new base plate project, and I'm going to open the toolbox, and under models, I'm going to search for Suphi. And here we should see some modules show up. And here we can see one module which is called Suphi's linked list module. And you need to also make sure it's from my username. So it should say 5UPHI here. And I'm going to click on this module over here. And it's going to give us a warning, and I'm going to say OK. And I'm going to close the toolbox. And here we can see the module. Now inside of this module, we have two other scripts. One that has some benchmarks, and one that shows examples of using the linked list. But I'm just going to delete these two scripts, and I'm going to rename this module into linked list, and I'm going to place it into server storage. Now what I'm going to do next is inside of serve script service, I'm going to create a new script, and I'm going to require the linked list module. So I'm going to say local linked list equals require gain server storage linked list. Okay, so now I'm going to open the linked list module, and I'm going to place this module to the right, like so that we can see it while we're scripting in our script. And we can see it has a new function to create a new linked list. So let's say local list equals linked list dot new. So inside of this module, we can see it has two classes. We have the list class and the link class. If we select list class, we can see all the functions for the list class down to here, and now it has link class, and these are all functions used for links. So now we have a list, we can use any of the functions inside of the list class. So for instance, we could use insert back, insert after, insert before, get next, and such. But let's insert to the back of the list. So there's two ways we could do this. First, we could create a link. Now links have to be tables, and then we can use list, insert back, and pass the link into this function. Now I'm going to call this link1. Now another way we can insert a link to the list is to say local link2 equals. Now if we look at insert back, we can see it returns the link that we passed into it. So we could say list insert back, and we could pass the table in directly into this function and get it back over here. So doing this and this are the same thing. Let's now add a value into our links. So I'm going to say value equals A. And inside of this link, I'm going to say value equals B. Okay, let's now say I want to insert another link, but I want it to go before link 2. So if we scroll down and we look at the link class, we can see it has some functions called insert before and insert after. So let's use this insert before function for the link class. So if we get link 2, we can see it has a function called insert before. So I want to create a new link to go before this. Now we can see that insert before also returns this link, so we can do it this way or this way. Let's do it this way. So I'm going to say local link3 equals, and I'm going to pass a new table into here, and I'm going to say value equals C. Okay, so now that we've created 3 links, let's iterate through the list. So I'm going to say for link in list, and I'm going to say iterate. We can iterate forward or backwards. Let's iterate forward. I'm going to say do, and I'm going to print the links dot value. Now if we run the game, we should see it prints A, C, and B. Now because link 3 was inserted before link 2, so that's why C goes above B. Just like iterating forward, we also have a iterating backwards function. So let's use iterate backwards and run again. And now we can see B prints first instead of last. So it's in the opposite direction. And it's also safe to remove and insert links while iterating through the linked list. So let's remove link 2 when we get to link 3. So what I'm going to do is say if link.value equals C, then I'm going to say link2 remove. So if we now run the game, we can see that once we get to link C, link 2 was removed, but because we already printed B, it's already too late. But if we change the order to iterate forward and run again, now we can see that only A and C get called, because when C got called, B was removed and was not printed. And it's also safe to insert links during iteration. So let's do a list insert back, but let's add a value of D this time, and let's run the game. And we can see it prints A, C, D. So when we got to C, it removed link B. So we can see B never got printed, and it inserted D, and we can see D got printed. But if we insert D to the front and run again, we should notice that it prints AC, but D never got printed because D was added at the top of the list, and we're already down at C, so D won't get printed. But if we loop through the list again and just print the values, and let me add a warning here. So warn, and let's just add some dashes, and let's run again. So we can see when we first loop through, it just prints AC, and D was added to the top. And then when we loop again the second time, because D was at the top now, we now see D when we iterate through. And finally, let me show you the remove up to function. So inside of the list class, we have a function called remove first, remove last, remove up to, remove down to, and remove all. And we can see that these remove functions are super fast. They only set 2 values within them. So they're very performant. So let's say that we have a list, and let's insert a whole load of lists inside. Let's delete all this. Let's make this A, B, C, D, E, F, G. And let's only save, let's save this link, so local link. And what I'm going to do is, once we've inserted them all, I'm going to loop through all of them. And then I'm going to use list, remove up to, and I'm going to pass in the link that we want to remove up to. And then I'm going to iterate and print them all again. And let's place a warning again. So warn dash dash dash, and let's run. So what we should see is on the first loop, we print from A to G. And then once we call remove up to, now when we iterate, it starts from D. So all these 3 values were removed very efficiently. And let's now try remove down to. So remove down to, and if we run the game again, now we can see it's the other way around. So from G all the way down to E was removed, and these values stayed in the list. And finally, let's take a look at remove all. So let's use remove all and run. And now we can see the entire list has been emptied. And there are some other functions, but I think I'm just going to leave it here. So here we can see that most of these functions are very simple to use and they're very efficient. We can see that most of them don't do much work within the functions. There, it's pretty efficient. And if you get stuck and you want to know how to use one of the functions, the best way to do that is to, when you get the module from the toolbox, is to take a look at the examples script. And here we go through almost all the functions available in the module. Thank you for watching my video, and if you have any questions, feel free to leave a comment down below.